Okay, hello Discrete Math. Hey, there are an infinite number of primes, have you heard? It's true. Let's prove it right now, and let's not be very careful at first, and then maybe decide to be careful later if we want to. So, okay, let's start. Are there an infinite number of primes? No, I guess, I'm sorry. Yeah, I guess there are. How can I show that there are an infinite number of primes? That's kind of a weird thing to do. How do you know that there are an infinite number of something? What does that even mean? Well, one thing you can do is maybe try a proof by contradiction. And this is the kind of thing, if you Google infinite number of primes, proof, you will find some proofs that kind of look like this. So let's go. Ready? Suppose that there are a finite number of primes. And then, here's what we're going to do. We are going to get some kind of contradiction out of this. Okay. Well, that will show that there are an infinite number, I suppose. Okay, let's begin the proof. Well, if there are a finite number of primes, then what are they? Well, let the finite number of primes be in some kind of set, P. So what's P? Alright, it's a bunch of primes. P1, P2, P3, etc. And, okay, let's say, that there are n primes specifically, and those are the ones. Alright, well, if you've seen this proof before, it's pretty famous. So, maybe you've seen it. If you haven't seen it, here we go. What you do is you take all these primes and you multiply them all together and add 1. So, alright, let's let this number q be the product of the primes plus 1. So P1, P2, P3, ... product is kind of intended here, Pn, but then plus 1. This is brilliant. What can we say about this number q? Well, yeah, here's what we can say about it. None of these primes divide q. Because, in fact, every one of these primes leaves remainder 1 when divided, when you divide q by any of these primes, what you actually get is remainder 1. So, it seems that we have some kind of a problem, because, well, what is this number q then? Okay, first let me just make this claim. My claim now is, by the way, I'm kind of setting us up a little bit for confusion, so I'm just presenting the proof that you often see on the internet. And whether that proof is good or bad, I think it's bad, but you might think it's actually fine. The claim is that this number q is a new prime not in set P. Claim q is a new prime not in set P. Why is this number a prime, and thus we have a contradiction, which is the goal. This is a proof by contradiction. Okay, well, yeah. So each, let's see, how am I going to put this? Each P sub I divides Q with remainder 1. You might just say, so it's just not the case that P sub I divides Q for any P sub I. And yeah, okay. So what? Yeah. Also, why is that important? Oh, yeah, and then also, of course, this number q, what? Also, q is greater than, oh, okay, so okay, so none of the primes divide q. Also, of course, that q is the product of the primes plus 1. So therefore, if Q is the product of the primes plus 1, Q is 1 more than all the primes multiplied by each other. And so, in fact, Q is greater than each of the p sub I. Alright, so what we have is this number Q, which is bigger than all of the primes in our set, but also doesn't have any kind of prime factor. Oh wait, doesn't every number have a prime factor? Yes. And so now we sort of take a closer look at this number Q. And we say Q is prime or composite. Well, both are a problem. Because if Q is composite, now I cite the theorem that we spent all day today proving, in fact, in 3 different ways, that every number has a prime factor. And so if Q is composite, then Q has a prime factor. In fact, every number has a prime factor. But none of the p sub I, are factors of Q. So we have kind of a contradiction there. That this number Q can't be composite because every composite number has a prime factor, and yet we've shown that from this finite set of primes, none of these primes divide Q. In fact, we constructed Q such that it had that none of these primes divided it. All right. So what's our conclusion? Q must be prime. So Q must be prime. And however, we already agreed. So I'll just say, but Q is greater than p sub I. For each I. And so Q is not equal to any of the p sub I, and yet this was supposed to be the full set of primes. So maybe one more way of putting it would be to say that Q is in fact not in this set P. And so we also have a contradiction. Both of these lead to a contradiction. If Q is composite, then it's supposed to have a prime factor, but none of the primes in this set divide Q. And on the other hand, if Q is prime, then we also have a contradiction because this is supposed to be the set of all the primes, and but Q is not in this set because Q is in fact bigger than all of these numbers. And so if it's composite, we have a contradiction. If it's prime, it's a contradiction. And yet both of them are one of those two must be true because composite just means not prime, and so we have a contradiction. And therefore, the assumption that there are a finite number of primes is contradictory, so there are an infinite number of primes. I did such a good job teaching that just now, sort of, that I've actually convinced myself that maybe this proof is kind of fine. And, alright, I would call this proof fine. That is to say, it's okay, and maybe it's not wrong. I don't know. Last year, the smartest kid in the class told me that he thought the proof was completely fine. So therefore, maybe it actually is fine. Maybe logically speaking, it's actually flawless. However, it is at least confusing. And it's at least confusing because I end this proof without the understanding of anything about this number Q. And, okay, what happens? We suppose that Q is composite. So taking a closer look now at the proof, now that it's over, we seem to look at the fact that Q is composite and got a contradiction. So just looking here, I have this statement: Q must be prime. All right, this has to be handled with extreme care. And okay, maybe if you're a very smart person and you're aware of all the little subtleties and your logical experience is high, maybe this proof is harmless. But for the people who are only half smart like me, this proof is dangerous because it seems that we've concluded that Q must be prime. And actually, there are just a whole lot of people out there who believe that the product of the primes plus 1 is actually necessarily a prime number. And, okay, and so it seems we've concluded that Q is prime, and the problem was just that that you know Q wasn't in our set or something like that. All right. I think this proof is kind of misleading, at least, if not sort of bad. Is it true that the product of the primes so far plus 1 is a prime number? Let's check it out. Let's see. Do I have room? I might have room if I start here and give myself enough room. Okay, so this is known as this is a kind of a well-known fallacy, and what have I written on my paper? Is Q prime or not? Well, first let's just establish some quick kind of facts. Quick fact number 1. What is the first Q1? Well, the first Q1 is the product of all the primes so far plus 1. What's the first prime? It's 2. So I guess that the first Q1 is the product of all the primes, so the product of the first 1 primes, which is just 2, plus 1, well that's 3. And 3 is in fact prime. So I'm feeling good. The product of the primes plus 1 is prime. Okay, what's Q2? Well, Q2 is the product of the primes so far plus 1. And in fact, 2 times 3, those are the first 2 primes, gives you 6 plus 1 is 7, and 7 is prime. So, looking good. What's Q3? Q3 is 2 times 3 times 5 plus 1. And what's that? Is 6 times 5 is 30, so that's 31. 31 is also prime. You might just know all your primes. But what about the product of the first 4 prime numbers? It's going to be, 2 times 3 times 5 times 7. Now the numbers are getting pretty big. I don't know, 35 times 6 or something. Can you do that in your head? Yeah, 211 plus 1, 210 plus 1 is 211. And alright, I don't know if you know these kinds of things, but 211 is in fact prime. So things are looking pretty good. Let me scoot over here because I need more space. What's Q5? The product of the first 5 primes plus 1. That's 2 times 3 times 5 times 7 times 11 plus 1. And what happens is you get 2,311. Just trust me. That is prime. If we were doing this live, I would tell you to, pull up some kind of is this number prime website on your phone or whatever and check it out. Alright, what's Q6? Tension is building here. 2 times 3 times 5 times 7 times 11 times 13 plus 1. You can just trust me or trust no one. Double check that this is 30,031. And this number is not prime. This number, 30,031, is in fact 59 times 509. Whoa. 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 Okay, so I don't want to, be responsible for misleading the youth, so I would just like to make it very clear right now that here is a math fact. The math fact is that the product of the first n primes plus 1 is not necessarily prime. It is for the first 5 of these numbers, and I forgot to Google this, but there is some kind of catchy name for this number Q, the product of the first n primes plus 1, but I can't remember what it is right now. What we get is that it's prime, it's prime, it's prime, it's prime, it's prime, and then it isn't. So that is kind of fascinating. It's possible that if you understood this proof perfectly, then you're not surprised. But it's also possible if you didn't understand this proof perfectly that you are surprised. Didn't we show that Q is prime? Well, not exactly. We showed that Q was not... Okay, what did we show? Well, the problem is this is not really a problem about prime numbers, this is a problem about our proofs by contradiction. And the problem with proofs by contradiction is that you assume something which is false. And once you assume something that is false, you're in some kind of absurd world where things have lost their meaning and everything is confusing and in fact everything is just wrong. And so we kind of met the bare minimum requirements of the proof by finding a contradiction, but once you do a proof by contradiction, you kind of enter a world of confusion and notice that we have this kind of theorem, this theorem that every number has a prime factor, which we proved not by contradiction. The theorem is just true. And yet, here I suppose that there were a finite number of primes. Okay, so what's really going on here is that there are sort of two uses of the word prime here. There's prime as in the numbers that are really prime. That's the meaning of prime in the world kind of outside our proof by contradiction. What does it mean for a number to be prime outside of our proof by contradiction? Well, it means that there are no factors that the number has no factors other than itself and 1. But then, because I'm trying to prove some fact about primes, that there are only a finite number of them, I've assumed temporarily that there are only a finite number of primes. And so now there's a kind of another definition of prime floating around here, which is that a prime number is a number of this set. And what have I really shown here? Well, let's see. I've shown that Q can't be composite, so it must be prime. But how did I show it can't be composite? I showed that it's composite because it doesn't have a prime factor. But I didn't really show that the product of the primes so far plus 1, I didn't show that the product of the first n primes plus 1 is necessarily prime. What I showed is that if there are a finite number of primes, then the product of the primes plus 1 is problematic in that it can't be composite because none of these numbers are factors. So, okay, I'm not explaining this very well, but I'm not going to go back and do this video again. Notice kind of what happened here is that if you take a look at 2 times 3 times 5 times 7 times 11 times 13 plus 1, you get this number, 30,031. How could this number not be, well, what can I say about this number? Well, it turns out, like, once again, math fact, it's composite. But what are the two factors of this, or what are the factors of this number? In fact, it's 59 times 509, and in fact, these numbers are themselves both prime. Okay, so the prime factors of this number are primes, but notice that they're like larger primes. They're not any of the primes 2, 3, 5, 7, 11, 13. And so, if you sort of now go through line by line the logic of this proof, this is better to do live, I think, but if you go back through line by line the logic of this proof, and each time you see one of these Q's, you sort of think of these specific Q's, Q1 through Q6 over here, then what do we, let's take Q6. What's up with this, this Q6? Do any of the numbers 2, 3, 5, 7, 11, and 13 divide this number Q6? Well, of course not. And therefore, since Q must have a prime factor, and yet we've assumed that these are all the primes, that's kind of the problem, right? Because while it's true that none of 2, 3, 5, 7, 11, and 13 are factors of this number, there are in fact kind of larger primes that are factors. Okay, so okay. I guess the point here is that we leave this proof with a kind of a misunderstanding of the nature of Q. Sometimes Q is prime and sometimes Q is composite. The contradiction arises from the fact that since we've assumed temporarily that this is the set of all the primes, and since none of these primes divide Q, we conclude that Q can't be composite. But it can't be prime either, because it's not on this list. Alright. Where is this all going? What? Okay. So, you could actually do this proof differently by instead of... So, okay, I don't want you... Basically, I'm ready to kind of move on now, I think. But I don't want you to get the impression that we've actually proved that this Q is prime. It's not. What we really proved is that it's just not composite. And so, it must be prime, and yet it's not one of the numbers of this set. You could also have taken this differently, and you could show that that Q is not prime. Why is it not prime? Because it's clearly not any of the members of this set. And so since it's not prime, well then it must be composite. And so you could also potentially walk away from this proof thinking that Q is composite. Okay, what is the takeaway here? I think that the takeaway here is that this is not the greatest proof. It does the job, but it leaves one confused. And that's because proof by contradiction are kind of confusing. And maybe should be avoided, sort of if possible. Because all we get out of the proof is the sort of is the results, right? The theorem only is what kind of falls out at the end, but kind of everything that we proved along the way inside of proof by contradiction is kind of useless to us, and maybe that's a reason to sort of not do proof by contradictions. Well, who proved that there are an infinite number of primes anyway? Isn't this like a Euclid thing? This is a Euclid thing. And Euclid proved this in a certain way that was not a proof by contradiction. So maybe we can get some kind of clarity on this matter by looking at Euclid's proof, which was not a proof by contradiction, and so we can actually learn something. So here we go. This is the Euclid version, which I think is just superior, sort of pedagogically and also just for basic understanding. And maybe just historically, it's just good to know that Euclid proved that there are an infinite number of primes, and this proof was his proof was not a proof by contradiction. How did he do it? Well, his theorem is not exactly that there are an infinite number of primes. Instead, it's that no finite list of primes is complete. No finite list of primes is complete. Okay, and so, all right, if you took logic, then you know something about this kind of subtle distinction between potential infinity and absolute infinity, actual infinity, I should say, and potential infinity. So the ancient Greeks were very careful to never talk about actual infinity. So you would actually never catch them saying anything like there are an infinite number of primes. Instead, they'll say something like, given any number of primes, there are always more primes. So the set of primes is sort of potentially infinite. And in fact, this provides a much cleaner proof. So, take some set of primes. So let P be just a set of primes. So this is going to superficially look a lot like the previous proof, but I'm going to be very clear that let P equal, let P be a set of primes. And now I make no claim that this is all of the primes. I just say, hey, take a set of primes. Well, I got a way of showing you that your list is incomplete. So now, the construction is exactly the same. This proof is due to Euclid, or at least we know it from Euclid, that you take the product of all the primes and all the way out to, once again, we have n of them plus 1. And now, what can I claim about this Q? The claim is, none of the P sub I divide Q. And maybe this time I want to be a little bit more careful about this reasoning. Why is that? Okay, well, suppose, for this part is a contradiction. Suppose that P sub K divides Q. For some, for one of these K. Okay, so just imagine temporarily, for the moment, that one of these primes in this set does divide Q. Yeah, no. Well then, because what do we have? Well, if one of them divides Q, then it means that Q can be expressed as, some number times pk. And you might say, with remainder 0 or something like that. But also, we have that Q can be written, well, here I'm going to factor out P sub k from the product of all these primes. And so we can write this as like, well, what is it? It's like, if I factor out a P sub k, then what's left, it's like P1, P2, P3, dot, dot, dot. And now, like, if you want to be clear about this, you kind of got to do one of these, like, pk minus 1, pk plus 1, and then dot 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 pn. So that's supposed to indicate that since you're listing the product kind of in order, that you've grabbed out the pk. Okay, and there it is, plus 1. Well, what have we just done here? We've just divided we've divided q by a piece of k, and we got on the one hand a remainder of 0, but on the other hand we got a remainder of 1, and so that's the kind of thing that we showed is just not possible. Okay, so this is a contradiction because by the Euclidean division algorithm, q cannot have two different remainders. Because by the Euclidean division algorithm, q cannot have two different remainders that are less than piece of k, that are less than pk when divided by pk. Okay, divide q by pk, and you will get some remainder, and you can get a remainder of 0 and also a remainder of 1. Alright, so that proves pretty rigorously that what is obvious, which is that none of these primes divides q. Okay, so what I'm now going to do, and I think this is what makes this proof of Euclid's a little bit superior, is I'm not going to make any claim about whether q is prime or composite, because as we've seen in general, you can say anything. But what do I know about q? Well, q must have a prime factor. This we proved today in class, that every number, whether prime or composite, has at least one prime factor. But none of none of the primes in P divide Q. Therefore, we conclude, so P is incomplete. Incomplete. And what we can now conclude, okay, this P was sort of arbitrary, right? So I sort of put maybe like a bracket around all of this, and my conclusion now is that so any finite set of primes is incomplete. Incomplete. I think this is a better proof. It's not a proof by contradiction, it's a proof by construction. Take a set of primes, but make no claim about whether this is all the primes or just a handful of primes, or just got like, some primes. And I got some primes. Hey, check it out. I made a number. Oh, none of the primes divide this number. And yet, every number must have a prime factor. Well, since none of these numbers divide Q, then you must be missing some primes. Because Q must have a prime factor, and yet none of these primes divide Q. So something is missing from your list, and therefore, given any finite set of primes, there are other primes that are not in this list. And sort of like, corollary or something, there are an infinite number of primes because no finite list of primes is complete. Okay, I like this proof a lot better, and yeah, I think it's just better. Okay, final thing to do, or, not or something. This is kind of, you can sort of think of this as an algorithm for producing new primes. And that is to say, when you construct this number Q, assuming you already kind of know how to perform prime factorizations in some ways, then you can use this number Q to kind of like generate new primes for yourself or something. So let's kind of erase this, and I'm going to make a little chart, and here is what this chart does. Okay, here's what this chart does. It says, okay, I got the primes so far. So I got some kind of set of primes so far. This is actually not so important. If you want to turn this video off, that's maybe like a good idea. Okay, or keep watching. What is this? This is Q. And what is Q? It's the product, so I'll use the fancy product symbol, of all the primes so far, plus 1. And then over here we have like our kind of answer or something of like, what happened? So what's the result? Okay, well, watch as I build some primes. Let's start with 2. That's kind of like the seed or something. So suppose I start with just 1 prime. Okay, well, let's take the product of the primes so far plus 1. Well, that's going to be 2 plus 1, and of course that's 3. And 3 is in fact a prime. So since this number is prime, I now add it to my list. And so I have like 2 and 3. Okay, now I take the product of the primes so far plus 1. Well, that's 2 times 3 plus 1. And that will give me 7. And 7 is, in fact, prime. So I got a new prime. 2, 3, and 7. Alright, let's take the product of 2, 3, and 7 plus 1. What do I get? I get 43. That is another prime. This is kind of an interesting way of generating prime numbers. This is a sort of a way of ordering the prime numbers that you don't typically think of. So I have 2, 3, 7, and 43. Those are my 4 primes so far. But if I now multiply 2 times 3 times 7 times 43 and add 1, what I get is 1807. And 1807 is not prime. It is in fact composite. And in fact, 1807 is 13 times 139. Okay, but every number must have a prime factor. And so, in the 3 cases we've seen so far, this number Q was already prime, and so we added that to our list of primes. But if our number Q was composite, it must have a prime factor, and by construction, this is what we did prove, especially this was clear in the Euclid version of the proof, that this number Q does not have any of the primes 2, 3, 7, and 43. None of those primes are factors of Q. So Q has prime factors, but it can't be any of those prime factors. It must be some sort of other prime factor. And in this case, it's 13. So I think that this is the sort of final maybe clarification of what's going on, which is that this is kind of an algorithm, so to speak. I mean, very loosely it's an algorithm because it assumes I know how to perform prime factorizations and I know how to check whether a number is prime or not. But it does kind of, the product of the primes so far plus 1 does kind of generate a new prime in the sense that it either generates a number which is prime or it generates a number which is composite, which has a prime factor, which has not already sort of appeared so far. And now we add kind of 13 to this list. So let's just keep going because I did all this work, so I might as well show it off. So I have 2, 3, 7, 43, and 13. That's my new prime. What happens if I multiply 2 times 3 times 7 times 43 times 13 plus 1? I get the number, big number, 23,479, which is again composite. What are its, what's the factorization? Well, 53 times 443. Actually, I have no idea whether these numbers 139 and 443 are prime or not, so let's just agree to take the smaller of the two. Let's make that the algorithm. But once again, 53 is prime, and it's a prime not appearing so far in my list. And okay, final row of the table, I got 2, 3, 7, 43, 13, 53. And if I take the product of all of those, 2 times 3 times 7 times 43 times 13 times 53 plus 1, I'm going to get like some kind of huge number. 1,244,335, which is composite, and which is in fact 5 times, you know, some stuff, like who cares? Okay, so it's only at this point that I get the number 5. Alright, so a new prime is produced at every step, but that new prime is either q, if q is prime, or a prime factor of q that not appearing so far. In other words, not one of these numbers. Alright, longest version ever. Some people do this proof in like 1 minute. For me, 25. Goodbye, everybody.